1 teaspoon of salt can be a great addition to your pasta. However, at the same time, when salting sidewalks, 1 teaspoon is enough to pollute 5 gallons of water. In Dane County, Wisconsin, due to the oversalting of sidewalks and roads during winter, salt concentrations in lakes and drinking water have been steadily increasing each year, harming aquatic life and worsening the quality of drinking water.
Now meet our team. My name is Paku.
I'm Ethan.
I'm Mikhail.
I'm JJ.
I'm Alexa.
And I'm Ashton. We are Penja.
As a team, we were tasked by the Wisconsin Saltwise organization to address this problem by developing a sidewalk salt spreader that can drop a uniform and consistent amount of salt according to the Wisconsin Saltwise standard.
Current salt drop spreaders drop an excessive amount of salt for two main reasons. First, the varying sizes of rock salt grains can jam the opening of a spreader, which forces operators to open the calibration to the largest amount, which thereby leads to more salt being dropped. Second, current salt drop spreaders have no method of accounting for the different walking speeds of operators, and therefore the salt drop rate is never consistent.
We first started with a brainstorming session. Throughout, we procured over 100 ideas, from a water wheel mechanism to control the salt drop rate, all the way to a completely autonomous machine that eliminates human error.
After multiple days of brainstorming, we narrowed our designs to the following. The coin sorter design tackles the problem of varying size salt grains through vertical sorting process. This design is a 3-tiered cylinder, where the larger grains get sorted at the top and the smaller grains can fall through to the bottom. The whole design would need to be 3D printed with precise hole sizes, and we would test this design through a series of trials, evaluating how successfully it sorts and consistently drops the salt.
The slant sorter design also employs a sorting process. As the salt flows down the slanted design, the smaller grains fall through first, then the second smallest, and so on. The sorted salt grains fall into buckets through which a gate will then release them to the ground. All the components would be 3D printed and laser cut. We would test this design also through a series of salt drop trials to measure the success of sorting and consistent spreading.
Next, the hopper churner design. Instead of sorting the salt, this design incorporates a churning mechanism that constantly moves around the salt to prevent large grains from clogging the opening.
Lastly, the speedometer design. This design would be attached to any of the previous designs. An operator would look at a speedometer to walk at a consistent pace. The speedometer would be purchased, and the testing of this design would need to include multiple trials to evaluate the efficacy of an operator continuously referring to their walking pace.
The hopper churner with an attached speedometer was agreed upon by the team as the most effective design, and after a presentation of each design to the class, the client had provided us with critical feedback explaining it would burden the worker to constantly look at the speedometer.
Given this feedback, we decided to finalize our hopper churner design. The hopper churner constantly moves salt pieces from the opening, preventing clogging. In addition, an electric sensor would detect the user's walking speed, and a motor would then adjust the gate to achieve the Wisconsin salt drop rate standard.
The team then moved in creating and executing a more detailed design and fabrication plan. We purchased an existing spreader that we could install our design into. Given its dimensions, we detailed thorough sketches of our design and created them on SolidWorks.
The first component, the rack and pinion, is composed of a gear and a horizontal surface with ridges. The motor would turn the pinion, which would in turn open or close the gate. This part was 3D printed out of tough PLA to withstand freezing temperatures.
Next, the gate itself, along with the base that would hold the gate, were laser cut out of HDF wood, which was optimal for our prototype.
Next, the churner mechanism was also 3D printed in 2 parts out of tough PLA.
Lastly, for the electronics portion, an Arduino was coded to calculate the velocity of the spreader to determine how far to open the gate, dropping salt to fit the Wisconsin Saltwise standard.
Before installing our design, we tested the current spreader. We first marked out a 60 by 18 inch rectangle on the floor as our salt drop region. We performed 30 trials at varying walking speeds.
Analyzing our recorded data, we concluded that with 99% confidence that the spreader drops between 585% to 830% more salt than the Wisconsin standard on average.
We then installed each design component into the spreader, using the same testing procedure to test our final design. After analyzing 30 trials of data, we computed with 99% confidence that the fabricated prototype dropped 70% to 97% less salt on average. The prototype is also within 80% to 150% of the Wisconsin standard on average, a significant improvement from the control.
To demonstrate the prototype, a user simply pushes the spreader. The hopper churner turns to move around the salt grains, and a motor will actively open or close the gate by measuring the user's walking speed every 5 seconds.
As a whole, the hopper churner successfully addresses the principal issues of varying salt grain sizes and differing walking speeds, and proves to have a major potential in counteracting the yearly increases of water salt concentrations. Our design will positively impact the quality of life for both aquatic creatures and humans.